Hello, my name is Paul Narguizian, and I am a professor of biological sciences at California State University, Los Angeles. My topic is on integrating complexity in biology education. The topic of biology is clearly a complex science. I will go so far as to say biology is probably the most complex science in the natural sciences due to its very nature of describing the emergent properties of life, and we biologists have yet to agree upon a definition of life, but that is for a separate discussion. This presentation discusses the historical development, describes the key characteristics, and presents some skills and competencies associated with complexity, emergence, and systems thinking. The primary goal is to provide biology educators with enough basic information about the four features of complexity utilized in big history so that they can consider why and how such an approach might be applied in the education of both biologists and a scientifically literate citizenry. In doing so, I will try to integrate the importance of complexity and systems thinking in biology education, with consideration given to the pedagogical underpinnings and science content in undergraduate biology courses. Before I dive into my work on how systems can unify biology and biology education, I wanted to take a minute and hear and acknowledge why biology, and more specifically, biology education, needs a unifying paradigm. It's probably no surprise to any of you, but we are dispersed across dozens of subdisciplines, and each of these disciplines uses different tools and methods, asks different questions, and that diversity is reflected in higher education, both in what and how we teach, and even how we're organized at our institutions. For example, here at my institution at Cal State Los Angeles, you can find biologists in various departments, colleges, and programs. And while diversity is great and wonderful, I'm a cell and molecular biologist by training, I appreciate diversity, but in education, it can make it challenging for learners to develop a really deep and coherent understanding of the discipline of biology. So during the past 10 years, a growing number of biologists and biology educators think biology needs a unifying paradigm, or in the words of Thomas Kuhn, a paradigm shift to support instructional design and curriculum development, while also enabling learners to organize their knowledge in meaningful ways that can support long-term retention and critical thinking skills. More generally, over the past 40 years or so, there have been and still are a diversity of voices in which there seems to be one common goal, all of whom seem to be describing, in various ways, systems, complexity, and emergence. Of course, each of these terms come heavily loaded with their own specific meanings and descriptions. Now, over a decade ago, the American Association for the Advancement of Science, or AAAS, in their Vision and Change report, identified a suite of core concepts for biological literacy. And after much discussion and debate, Vision and Change participants agreed that all undergraduates should develop a basic understanding of the following core concepts, what Mommsen and her colleagues call the Big Five, from evolution to movement of matter and energy. This represents a major step forward in refocusing biology instruction away from memorizing kind of the litany of facts towards developing really deep and meaningful conceptual knowledge. The five core concepts that you see represented here were presented to our community here in the United States as a starting conversation. This was not seen as the end of the conversation, but a way of getting us to think more deeply of what biology is really all about at its core. And one thing you'll notice is that the Vision and Change presented these foundational concepts as discrete. There's no organizing framework that links or connects these concepts to form an integrated whole. So my research started looking at systems as a potential unifying paradigm for biology teaching and learning. And why did I focus on systems? Well, for a few reasons, which I will outline in the next slide. Systems theory has diverse roots in biology itself, but it also emerges out of big history and a lot more disciplines, right? So diverse roots makes this a promising idea or concept to be elevated to this paradigm status. And when we dig into the literature across biology, big history, and cognitive psychology, I took a look at some of the definitions of systems, and they all resonated with the overall theme of biology and big history. There were also a lot of parallels and similarities across these definitions of what is a system. It's the idea that they're groups of interacting elements, components, or structures that form a whole with a particular function. And if we think where specifically in the 21st century and biology, systems is increasingly important to us. We took a reductionistic approach early on in the discipline of biology, trying to unpack and understand all of the parts of living things. And now we're putting all those parts together to make this broad understanding of big history, of big systems, or what I like to refer to as big biology, and what's happening more complexly. And there is, as a result, a broad literature base that describes system thinking skills. So, with these ideas in mind, I like to revisit the big five core concepts in vision and change and explore how we can reorganize them to use systems as that organizing paradigm. So, let's first consider biology as the study of living systems. I hope we can all agree that that's what we do as biologists. And we can provide organization to these core concepts by then thinking about that. Some of us are very interested in studying the structures that comprise living systems, and others are interested in how the structures of living systems interact to move or transform information or matter and energy. These are the functions of living systems that, if we talk to most of our colleagues, is kind of what we're researching these days. We might also explore how living systems interact within response to their environments, and that results in emergent phenomena like evolution and homeostasis. So now that we have an idea for how systems could form a paradigm to organize biology and biology education, we then turn to thinking about our instruction, utilizing the four features of complexity featured in big history, so that we can consider why and how such an approach might be applied in the education of both biologists and a scientifically literate citizenry. Traditional instruction isn't organized around systems or systems thinking. As a matter of fact, the majority of undergraduate course syllabi for both non-majors and majors introductory biology courses are organized from little biology to big biology, or the core concepts have been separated and divided up across introductory course content and syllabi. While the reductionistic approach has resulted in a significant increase in our knowledge of the natural world, and in great technological advances, it is not sufficient for addressing global world challenges such as climate change, sustainability, habitat destruction, and social justice. And part of that is because we don't take the systems approach because we lack the tools to really integrate systems thinking into our classrooms. And that's what I hope this integration of biology systems thinking and the four features of complexity framework described in big history can help us by supporting learners and as instructors. In the systems thinking hierarchical model, or STH, represented here in figure 2 from Orgill, York, and MacKellar, this represents the 8 systems thinking skills, which are further divided into 3 levels. Level 1 includes analysis of a system components. Level 2 includes synthesis of system components. And level 3 includes implementation. From the bottom of the model, the first level, analysis of system components, includes only the first systems thinking skill, which is the ability to identify the components of a system and processes within the system. Synthesis of system components, the second level, encompasses systems thinking skills 2 through 5, the ability to identify relationships among the system's components, the ability to identify dynamic relationships within the system, the ability to organize the system components and processes within a framework of relationships, and the ability to understand the cyclic nature of systems. As you can see, topping the pyramid is the third level, implementation, which includes the final 3 systems thinking skills: the ability to make generalizations, understanding the hidden dimensions of the systems, and thinking temporally, retrospection, and prediction. A proper understanding of living systems and complexity, or biocomplexity, I will use these 2 terms interchangeably, and I should note here that I will not provide a specific definition of the term complexity since academics and scholars have yet to agree on a definition, so that an understanding of living systems and complexity, or biocomplexity, requires much more emphasis on the synthesis and integration of information from across temporal, thematic, and spatial scales. This new perspective recognizes the interactions in biological systems, the connectedness between biological systems and their physical environments, and the complex properties that emerge from the interplay among the biological and environmental components. As was also stated earlier, biology educators require a new paradigm in order to integrate the reductionistic approaches that are commonly used in biology research and education, with a complementary holistic approach. Complexity, emergence, and systems thinking is such an approach. A foundation in systems thinking includes biocomplexity, which again emphasizes the interconnectedness and interactions within biological systems. By incorporating this approach into biology education, students can develop a holistic understanding of how various components of living organisms and ecosystems function together, while at the same time applying the various parts of the system to the whole. They can analyze complex biological phenomena and appreciate the importance of interdisciplinary perspectives. David Christian and his colleagues have developed various curricular tools to assist students with deciphering systems and their associated complexities within multiple natural science content areas. These include cosmology, physics, chemistry and biochemistry, geology, biology, etc. In all of my courses, including lower division and upper division biology courses, I have included this info card for students as a formative and summative assessment diagnostic tool to gauge their deep level understanding and comprehension of various student learning outcomes and/or course objectives. My particular focus, of course, from Big History is centered around Threshold 5, or life. This info card summary provides my students with basic foundational content knowledge. However, the goal is to expand on this by diving deeper within each biological system being uncovered within each specific biology unit listed on the syllabus. Here, one can notice a bit more detail being discussed. Again, at this point, it is up to the instructor and the students to add to the various features in order to address the specific content or system being covered in class. The overall goal with my research is to maintain the scientific biological narrative of the big 5 core concepts discussed earlier from the Vision and Change document. Mommsen et al. Has laid out the basic foundation for incorporating systems thinking in biology courses by defining the interrelated components of systems into 4 different levels described here. The challenge remains to transform these into a workable document for teachers and students alike to use in each unit being covered in the course. One such tool I have used in the past has been this formative and summative diagnostic tool. Here, students work in groups to pinpoint the specific threshold or system of interest at the top, followed by discussing and inputting the specific ingredients, the Goldilocks or ideal conditions, and the complexity which emerges from them both. This allows for a deeper in-class discussion, along with addressing a few student misconceptions which can arise. My research is still ongoing, and I hope to have a tool developed and tested, such as the one shown here, in the near future. Of course, there are still open questions that will need to be addressed. These include, what are the appropriate benchmarks toward development of ST or systems thinking skills? Which systems thinking skills are most difficult to acquire? Could a systems thinking learning progression be developed for undergraduate biology? What kinds of assessments or instructional practices best promote and reveal different systems thinking skills? How would a systems thinking paradigm impact curricular development? And finally, what may be the long-term outcomes of students' engagement with systems thinking? Thank you for watching, and I look forward to our discussions during the live panel discussions and conversations.